So over the past 5 lectures, we have gone through a probability review. We started from the very basics. We talked about set theory. We talked about essentials of random experiments, probability axioms, calculating probability through combinatorics, and we continued with that until we got to random variables. We discussed random variables, a single random variable, famous discrete random variables, and continuous random variables. Today, we will take this a step further, and we start discussing pairs of random variables. Let's start with the discrete case. The marginal probability mass function, Px of x, is the summation over y, the joint, and the same for Py of y, summation over x, the joint. The probability of the pair x and y being a point in some plane B is the double summation of x and y belonging to this plane B, Pxy of x and y. The same for continuous random variables, but instead of the summations, we do integrations. And instead of the PMFs, we do PDFs. Integration over x, fxy of x and y dx, and the probability that the pair x and y is in some plane B is the double integral over a plane B, fxy, x and y dx, dy. So when we look at the joint probability mass function, the joint probability mass function is a function describing how two random variables are changing together, how two random variables are behaving together, are behaving in a combined manner, all right? If they are independent, then this Pxy of x and y becomes Px of x times Py of y. It's just that the probability that the first random variable equaling specific value multiplied by the probability of the second random variable equaling a specific value. Here you are doing the process of marginalization. Logically speaking, you want to get the PMF of one of the two random variables, say x, so you are just summating over all the possible values of y to cancel y out, all right? The same logic applies also for the PDF, so the one different that this is a density, not a probability. These two relations are quite important, so if you want the probability that your pair x and y are in a specific plane B, here and here you perform a summation, here you perform an integration. Whatever lies underneath the summation units or the integration units is always probability, okay? So if you have functions of random variables, and you are trying to calculate certain probability, what lies here is probability. The function will only show up here and here, will not show up here. This is always the joint PDF, the joint PMF or the joint PDF. Observe the subtle difference between the two cases. Here, x and y are discrete random variables, so you're talking about a point, so you are checking on whether a point belongs to a plane. Here, you're not talking about a point, you're talking about the area of an entire plane altogether because you cannot handle it point by point. One simple example is you can look at something like the one in the notes, and this is the plane of B. In the discrete case, you will be operating on all the points inside this area. In the continuous case, you are integrating on the entire area. All right, everyone's okay with that? All right, good. Some useful CDF relations. The marginalization of the CDF and the marginalization for y is fxy of infinity and y. Can someone tell me why is that? Or what does that mean, logically speaking? What does it mean when we set y here being infinity?
So y is less than infinity, so it's the exact case.
Yeah, so essentially, logically speaking, like what you said, it is as if you are doing this, right? In the end, this is a probability, not a density. So when you go until infinity for one of the two variables going backwards, right, then you are taking all the possible values of y, and thus you are marginalizing y. And it is the same case for x, right? Two more also very useful relations, fxy of x and minus infinity, fxy of minus infinity and y. What do you think these two will be? Why? Yeah, exactly. It's the opposite from what we were doing. So in that case, you are going from infinity backwards. Well, this is really non-rigorous thing because infinity is not a number, but just for the sake of illustration. And here, there is nothing to go backward from, right? So when you set minus infinity for one of the two variables, this immediately gives you a 0. Now let's suppose we want to calculate the joint CDF for point x2, y2. Well, actually a range. Let's set it to be a range. x1 less than x less than or equal to x2. y1 less than y less than or equal to y2. Where we are in this area, this is our x, this is our y. This is the point x2, y2. This is the point x1, y1. And we want to calculate this probability from the CDF. So what is this probability? We want to calculate this probability through the CDF. So this probability corresponds to what plane on this plot we just had drawn? Let's do it step by step. So this probability corresponds to which area on this? Exactly, it's the upper square, right? It is this area. So this area can be obtained by fxy of x2, y2 minus fxy of x1, y2 minus fxy of x2, y1. Is it all? What did we do here? Got all this area, subtracted this area, subtracted this area. Is it enough? Why? Exactly. Which one should we add then? This one, right? So plus fxy of x1, y1. Okay, why didn't we put equality here and here? Because still xy, x1, y1 itself is subtracted, right? It is involved here and involved here. So it is subtracted twice, and then you added it, but it is still subtracted, right? Remember always that the CDF is continuous from right and above, from after the points, after you get the points, right? Okay, if this was a continuous case, we can easily put them back because the probability of a single point is 0, right? Whether it is continuous, discrete, doesn't matter. All right, good. Let's do an example. A modem transmits a two-dimensional random signal xy as follows. x equals r cosine 2 pi theta over 8, y equals r sine 2 pi theta over 8. Theta is a discrete uniform RV in the set S equals 0, 1, dot, dot, dot to 7. And then we have some questions. Find, let's write find here. Find the mapping S to SXY. Find PXY of x and y. Find Px of x, Py of y. And find the probability of these events. A equals x equals 0. The probability of y less than or equal to r over square root 2. And the probability that x greater than or equal to r over square root 2, y greater than or equal to r over square root 2. Okay. So at this moment, we will leave probability for just some time and try to discuss something, and then we will return again. Let's assume that this theta is a continuous parameter. Forget about the whole random variable thing and probability. It's just a continuous parameter, okay? So obviously these two functions are periodic functions, right? When you multiply these two functions together and make an integration over a period or multiples of a period, what will the result be? What's up? Who said 0? Yeah, right? When you multiply cosine and a sine, gives you sine double the angle. Double the angle means compression. You integrate it over the period, it gives you a 0. What does that mean? It means that these two signals, if we replace theta by a time variable, are orthogonal, right? When we return to the shape we have here, these are just a bunch of values according to the value of theta, the discrete value of theta that takes a value from 0 to 7. So let's assume that we load them over two similar functions, but with a time variable, two orthogonal functions. And let's call them phi 1 and phi 2. So phi 1 is for x, and phi 2 is for y. So the value in the direction of phi 1 will be x. The value in the direction of phi 2 will be y. These 8 points, according to S, will look like what on this plane? What's up? Thank you. Exactly, right? They will look like a circle around the origin, right? 1, 2, 3, 4, 5, 6, 7, 8. Right? This is how they will look. This is not the best circle in the world, but yeah. All right. So this is actually one of the most famous modulation schemes. And it is used in a variety of applications in baseband transmission, in passband transmission, and it is called the phase shift keying, PSK. Phase shift keying. Why is it called phase shift keying? Where is the information stored here in this shape? How can you differentiate between 2 points? What is the difference between this point and this point, for example? The angle. The only difference between them is the angle, right? So you are not putting any information in the amplitude. You are putting all the information in the phase. So this is called phase shift keying, and it is a famous way of transmitting information. But a side point to mention is it's not the most efficient when you have more and more numbers. The idea is it always puts all the points on a circle. So let's assume that you have 16 points or 32 points. In that case, the point become closer and closer to each other on the arc, right? And thus the probability of error becomes higher. So when you get noise, it becomes easier to confuse them. It becomes easier to go from here to here or from here to here. And why is that? Because the logic in that case is that you have all this like huge area of energy and you are only using all the points on the arc to store the information. So that's why there are other more efficient types of modulation when you have higher modulation schemes that essentially put points in the middle to increase the distance between them. All right? Is it clear? Okay. Let's now return to probability and try to do this problem. So the first question asks how to convert the sample space S of the random variable theta into the sample space Sxy of the combined random variable. So we can do it quickly together. So Sx of 0 is Sxy of what? You can just like look here and tell me the answer immediately. Exactly, R and 0, right? How about S of 1? Is this guy, right? What is this guy in terms of X and Y? Exactly. R over square root 2 and R over square root 2. S2 is Sxy of 0 and R. S3 is Sxy of minus R over square root 2 and R over square root 2, dot, dot, dot. Okay, the rest you can easily complete. Let's move to P. What is the joint PDF between these two random variables X and Y? This guy is a discrete uniform. We substitute all of its different values in order to get the possible values in the sample space Sxy of X and Y. Is there any point that has any preferential treatment over any other point? No, right? They're all the same, right? Since they're all the same, what is this guy? Exactly. It's 1 over 8 for all of them. 1 over 8 for all xy such that xy belongs to Sx and y. All right, let's do the marginal. Before we do the marginal, let's put the sample space of X. What is the sample space of X? What are all the possible values X can take? From here, right? It's this value, this value, this value, this value, and this value, right? What are these? Exactly, minus R. Minus R is the smallest, actually. Or minus R over square root 2, 0, R over square root 2, and R. Is there any preferential treatment among these points? Are there some points being repeated versus oh, in this case, yeah, this is tricky. So let's write it. So Px of X is gonna be what? How about the point X equals R, this point? Is it repeated? No, this one is not repeated. So it's 1 over 8 for this case. How about the point minus R? That was the same thing, it's not repeated, right? So in this case, we could say that at theta, or X, I should say, X in minus R and R. How about the 3 other points? Yeah, each one of them is repeated twice, right? So for the other 2 points, it's 2 over 8 or 1 over 4, where X belongs to minus R over square root 2, 0, R over square root 2. Let's calculate some probabilities quickly. What is the probability of the event X equals 0? we just did it. So there is nothing to do here. What is the probability of the event x less than or equal to r over square root 2? X or y, here in the problem statement it is y, but it really doesn't matter because actually PMF of y is the same. How about this probability? How can we calculate it? What is the only point we are missing up here? Right? So it is just 1 minus the probability y equals r. It is 1 minus 1 over 8. It is 7 over 8. And the last one was the probability that x greater than or equal to r over square root 2y greater than or equal to r over square root 2. How many points represent this situation? Only one, right? Because whenever you increase x to become r, you will never have y greater than 0, right? It doesn't happen. And the same for y. So this is only a single point, and since it is a single point, we can write it as the probability that x equals r over square root 2, y equals r over square root 2 equals 1 over 8. All right. Any questions until now?
Why did you write P1 and P2 instead of X and?
Why did I write what?
P1 and P2 at the problem.
Yeah, it is because these are not, these are discrete signals, right? We wanted to load them on continuous signals to perform a transmission. In the end, you transmit something like this, right? Either a sine or a cosine. Okay? So we loaded them on orthogonal time domain signals, and these will just determine the magnitude and phase of the constellation point you will put in the space. Okay? Great. Let's do another problem, but this problem will be a continuous problem. Example 2. The amplitudes of two signals x and y have the joint PDF fxy of x and y equals e to the minus x over 2y e to the minus y squared for x and y greater than 0. We want to find the CDF, the joint CDF fxy of x and y. We will want to find the probability that square root x is greater than y, and we want to find the marginals that are fx of x and fy of y. How could we find the joint CDF? How could we find the joint CDF? Exactly, integrate. So fxy of x and y is the double integral from u equals 0 to infinity, from v equals 0 to infinity. Well, not to infinity. Exactly, thank you. So this one is x and this one is y. E to the minus u over 2v e to the minus v squared dv du. Why did we replace the variables of the joint PDF to be u and v? Yeah, exactly, right? This thing should end up being a function of x and y. So the variables you are integrating on will go away, and x and y cannot go away. Those are your function, essentially, right? So since x and y appear outside, you've got to change the limits inside. How can we deal with this integration? So let's first simplify it a little bit. From 0 to x, e to the minus u over 2, the integration from v equals 0 to y, v e to the minus v squared dv du. How can we deal with this integration? It is much easier than doing it by parts. This one is easy because you could see that if you write this as from u equals 0 to x, e to the minus u over 2, from v equals 0 to y, and you do something like this. So you already have d e to the minus v squared with you, right? This is the differentiation of dE to the minus v squared is 2ve to the minus v squared, right? With a minus sign. So you immediately can write this from 0 to x, e to the minus u over 2. This thing is e to the minus v squared over 2 from v equals y to 0 du. This gives you half 1 minus e to the minus y squared. The other integral is even easier. From u equals 0 to x, e to the minus u over 2 du. This one we can even do immediately. It will give you 2, 1 minus e to the minus x over 2. So the final answer is 1 minus e to the minus x over 2, 1 minus e to the minus y squared for x, y greater than 0. All right. We got some CDF. We want to check it. So let's substitute some CDF properties. fxy of x and minus infinity. This thing is supposed to be 0. Or let's do the other way around. Yeah. Of infinity and y. This one is supposed to be 0, right? Will it be a 0? When you substitute x is minus infinity here, will it give you a 0? No, right? Oh, so this is not a CDF? What's the problem here? fxy of minus infinity and y does not give us a 0. Thank you. Here. The problem is here. Okay? Minus infinity is not a valid point for this function, for neither x nor y. So, the alternative value we should check here is, what is the very first point we should check here? It is the 0 itself. Will fxy of 0 and y give us a 0? Absolutely, right? And the same for fxy of x and 0 will also give us a 0. All right? Good. Let's do the next one, which is a probability of a specific function. So we have the probability that square root x is greater than y. Let's draw this plane and see. So we have y equals square root x. So the area we are trying to integrate here is the area above that curve or underneath that curve. Exactly, right? It's the area underneath that curve. It is this area. When we take our infinitesimal stripe here, we can immediately try the integration. In this case, it would be the double integral over x and y. What do we have here? The original PDF, which is e to the minus x over 2y, e to the minus y squared dy dx. Can someone help me with the integration limits? X from what to what? Y from what to what? According to this stripe. Exactly. How about x? Exactly. Thank you. Right? We notice here that this will end up being some probability, will end up being some number. So x and y will go away, so you have absolutely no problem that you use them inside the integral, right? First, you will cancel out y, put x. Second, you will cancel out x, put the limits. So in the interest of time, there is no need to go through this integral in detail. It will end up being something like this, half 2 e to the minus x over 2 minus 2 over 3 e to the minus 3x over 2. That will end up being, from infinity to 0, half 2 minus 2 over 3, which is 2 over 3. All right. Let's do the last part where we want to get the marginal PDFs fx of x and fy of y. How can we get the marginal PDFs? Yeah, you can actually differentiate the CDFs, but unfortunately, until now, you don't really have the marginal CDFs to differentiate, right? We have the joint CDF. That's what we have. How can we get the marginal CDFs from it as a first step, and then we apply what our friend here said? This is the joint CDF. We have it here. He said we differentiate the marginal CDFs. How can we get the marginal CDFs from the joint CDF? This is already a probability or integrating, remember?
We implemented the y in the joint PDF to get the marginal PDF, then differentiate it.
So your ultimate goal is already the marginal PDF. That's what you want to do. What's up? Yeah, thank you, right? This one is, it's actually one of the cool problems to apply this. Because once you put any infinity, you cancel one of the two terms, you have the other one, you differentiate it one step, boom, done, right? So fx of x is fxy of x, and infinity is 1 minus e to the minus x over 2. And thus fx of x is d by dx fx of x capital, which is half e to the minus x over 2x greater than 0. And then you have fy of y in a similar manner, fxy of infinity and y, 1 minus e to the minus y squared. Fy of y is y, 2y e to the minus y squared, y greater than or equal to 0. What is this here? This is referring to what random variable? Exactly, right? This is an exponential random variable with lambda equals a half. All right? Okay. Anybody's having any issues until now? Most good? Great. Let's pass by a jointly Gaussian random variable. Jointly Gaussian RVs. And let's write this fantastically long formula. 1/2 pi sigma x sigma y square root 1 minus rho squared, the exponential of 1 minus, let's write this part here, minus 1/2, 1 minus rho squared dot x minus mx over sigma x squared, y minus my over sigma y squared, minus 2 rho x minus mx over sigma x, y minus my over sigma y, and brackets, and this is x. What we want to discuss here briefly is not particularly all the properties of jointly Gaussians, because we talked about jointly Gaussians before when we talked about correlation and independence and so on and so forth. Question for you, what happens when we put this row equals 0? Well, why do you ask that question? Not necessarily. You have one of them being mx as its mean and one having my as its mean. Not necessarily. It can be 0, it can be anything else. What happens when we put this row 0?
It resembles to normal graph.
Right? Okay? So when we put row equals 0, this fx and y of x and y resembles two independent Gaussian random variables, as our friend said, where fxy of x and y is fx of x times fy of y. That is absolutely correct, and this gives us the intuition that what is this row? This row is actually the correlation coefficient between the two of them, okay? Which we will talk about soon. Rho is the correlation coefficient. All right, let's talk about the last thing in today's lecture, conditional PMF PDF and expectation. P x given y of x given y is pxy of xy divided by py of y. F x given y of x given y is fxy of x and y divided by fy of y. You can do the same thing for x. There is no need to really repeat this. This thing is nothing new to us, even in this course, right? We have seen something like that already, but in the language of events. It doesn't matter, right? Random variables equaling a specific value can be seen as an event as well, right? It is the event that the random variable equals this value. So you can also understand the conditional PMF, particularly because it is a probability. The conditional PDF is a density, so it's a little bit of a different story. But you can understand the conditional PMF as also a relative frequency, right? You remember when we did this before? NA intersect B divided by NB. It could be seen also as a relative frequency, right? Of an event, x equals something, x equals small x, y equals small y happening together in the circumstances where y equals small y happening, right? And then we also have the expected value of y given x, the conditional expectation, the integration over y f y given x of y given x dy. And also, obviously, this is in the continuous case, so we sum if discrete. All right. We will discuss also some very important theorem, which is the expected value on x, the expected value of y given x is E of y. First of all, I put x here. I didn't put any variable here because here it is understood by default that you're talking about y. It is variable y conditioned on x. Here, nothing is understood by default. It's the expectation of something that has inside it some y's and some x's. So you got to put the PDF or PMF you're referring to outside here. So this is Ex of E y given x. First of all, have we seen something that resembles this relation before? Yeah, this is the total expectation. That's correct. So what did we see that is quite similar to this thing? It's called total something as well. Right, yeah. This is quite similar to the total probability theorem. It's the exact same logic. You also partition the space into multiple areas. Each area takes just a value for x, and then you make the expectation on all of them to get E of y. The exact same logic. What was the total expectation theory? It was that you can get probability y equals y from the summation over x p y given x of y given x times p x of x. Right? What is this? Can't I write this as this guy? I can, right? So this guy is absolutely this guy, right? So one of them is the total probability theorem, and our friend said this is the total expectation theorem. We can prove it. Proving it is not that hard at all, so let's do it together. Proof. This expectation Ex of E y given x is integration over x, integration over y f y given x of y given x times fx of x dy dx. You can change the order, make it integration over y, then integration over x, f y given x times fx of x dx dy. What is our friend here? What's up? All together it is, yeah. That's correct. So I wanted to do it on 2 steps, but your final answer is right. So first it is the joint, and then you integrate the joint on x. It ends up being the integration over y fy of y dy, which is E of y. Remember that we have seen this total expectation just on Tuesday, right? In the problem of successive coin tosses. It was solved by the total expectation theorem, right? Okay. One last thing. What is the expected value of x given x. Obviously here we did it for the continuous case, but you can also sum for the discrete case. What is the expected value of x given x? Someone said something? So someone said something correct. What is the expected value of x given x? Someone needs to answer this question. Stay here until tomorrow. What's up?
I just want to see what it looks like.
Random variable x.
Right. So the answer is x, right? So your answer has two parts. Part is perfectly correct, and part, it was a random variable. Right? Not anymore. But your final answer is correct. The expected value of x given x is x. Why is that? There's no more randomness. This is becoming the expected value of a constant. It's the expected value of a random variable given I gave you the random variable. Where is the randomness? Right? So the expected value of x given x is x. As a matter of fact, this applies also to the expected value of any function that is solely of your random variable is also x. For example, the expected value of x squared plus x plus 1 given x is x squared plus x plus 1. There's no randomness. I gave you its value. It's nothing. Right?
Can you show explicitly? I can't see clearly. I didn't understand.
Let's assume that you have a random variable x. Let's do a discrete example. You have a random variable x that takes a value from 0 to 10. Okay? And I just you are guessing the value of this random variable. I open the door, I tell you, hey, x is 5. So what is the expected value of x given that I told you x is 5? And there is no random variable. Now x is 5. The answer to this is 5, right? It is x itself, and it is no more a random variable. Right? Okay, so